Hello, in today's lesson we're looking at graphing logarithmic functions and its inverses. Our essential question is, how do you graph logarithmic functions and its inverse? A logarithmic function is the inverse of an exponential function. On the right, you will see the graph of the exponential function y equals 10x and its inverse y equals log of x. You'll notice that the two graphs are a reflection of each other across the line of symmetry y equals x. You can also tell from the points on the graph that they are inverses. At x equals 0, y equals 1 for the exponential function, and on its inverse, we have x equals 1, y equals 0 for the logarithmic function. At x equals 1, y equals 10 for the exponential function, and its inverse has x equals 10, y equals 1 in the logarithmic function. Exponential functions and their transformations have horizontal asymptotes. The equation for the horizontal asymptote of the graph of the parent function is y equals 0, which is the x-axis. The graph is never parallel to the horizontal asymptote, but moves toward it at a steady pace. Logarithmic functions and their transformations have vertical asymptotes. The equation of the vertical asymptote of the graph of the parent function is x equals 0, which is the y-axis. The graph is never parallel to the vertical asymptote, but moves toward it at a steady pace. Graphing a logarithmic function and its inverse. What is the graph of y equals log base 3 of x? Describe the domain and range and identify the asymptote. Since this is a logarithmic graph that doesn't have anything added or subtracted to it, I can say that this is my parent function and my asymptote is a vertical asymptote at x equals 0. To graph this function, I'm going to choose points that are to the right of my vertical asymptote. I'm not going to choose points to the left of my vertical asymptote because the logarithmic graph will be undefined at any point to the left of the vertical asymptote. So here's my table of values, evaluated each of the x values in my function and got at x equals 0.25, y is equal to negative 1.3. At x equals 0.5, y is equal to negative 0.63. At x equals 1, y is equal to 0. At x equals 2, y equals 0.63. And at x equals 3, y equals 1. Graph my function to get this graph over here. Notice how my logarithmic function gets closer and closer to my vertical asymptote but does not pass the vertical asymptote. And I don't have any graphs that are on the right of my vertical asymptote. Our domain for x goes from 0 to positive infinity, not including 0. The reason why I'm not including 0 in my domain is because if I evaluate log base 3 of 0, I am going to get an undefined value. I also know that my graph gets closer and closer to 0, but never really crosses it. My range goes from negative infinity to positive infinity, so I can have negative values for y. I can even have positive values for y, knowing that this graph is going to go on and on forever in the positive x direction, and the value for y increases in the positive y direction. Now let's take a look at the inverse of the graph of y equals log base 3 of x. First, we need to find the inverse of our log function. To do that, I'm going to switch my x and my y so that I have x is equal to log base 3 of y, which I can rewrite as log base 3 of y equals x. From here, I'm going to do the loop to rewrite this in its inverse, which is an exponential function. Starting at 3, going through x and all the way to y, I get 3 to the power x equals y. So the inverse of my function y equals log base 3 of x is 3 to the power of x. Since this is an exponential function and I have nothing added or subtracted to my 3 to the power of x, I can say that this is a function where the horizontal asymptote is at y equals 0. To graph this function, I'm going to do an input-output table, and I got at x equals negative 2, y equals 0.1, at x equals negative 1, y equals 0.3, at x equals 0, y equals 1, at x equals 1, y equals 3, and at x equals 2, y equals 9. Plotted the points And here is our graph of the inverse of the logarithmic function, which is y equals 3 to the power of x. Let's talk about the domain and range for our inverse. Our domain goes from negative infinity to positive infinity because I can put all values for x, the negative values for x and the positive values for x. Our range goes from 0 to positive infinity because our graph never crosses the x-axis. It gets closer and closer to 0 but doesn't cross it. And then as our x values increase, our graph goes towards infinity. In the domain and ranges, you can see that there is a switch of our domain and range. In the logarithmic function, our domain goes from 0 to positive infinity, whereas in its inverse, the range goes from 0 to infinity. In the logarithmic range, it goes from negative infinity to positive infinity, whereas in our inverse, the domain goes from negative infinity to positive infinity. Here is a better look of the log base 3 of x and its inverse 3 to the power of x. The function y equals log base b of x is the parent for a function family. You can graph y equals log base b of the quantity x minus h plus k by translating the graph of the parent function y equals log base b of x horizontally by h units and vertically by k units. The a in y equals a times log base b of x indicates a stretch, a compression, and possibly a reflection. In this table, you see all of the transformations that can occur to the parent function of the log. If a is greater than 1, it stretches it. If a is greater than 0 but less than 1, it shrinks it. If a is less than 0, it is a reflection in the x-axis. A translation occurs horizontally by h and vertically by k. And this is what it looks like when it's put all together. Translating y equals log base b of x. How does the graph of y equals log base 4 of the quantity x minus 3 plus 4 compare to the graph of the parent function? From our function, we can see that we have a horizontal shift over here at x minus 3, so I need to figure out what my shift is. To find h, set x minus 3 equal to 0, solve for x, we get that x is equal to 3. So we have a horizontal shift to the right by 3 units. Our k value is this positive 4 over here, so we have a vertical shift up by 4 units. I do not have an a value, so there is no reflection or dilation of this graph. Since my parent function has been transformed, my vertical asymptote has also moved. My original vertical asymptote is at x equals 0. Now my vertical asymptote is at x equals 3. To graph the function, I am going to create an input-output table and choose some values to the right of my vertical asymptote. I chose values for x and evaluated my function y equals log base 4 of the quantity x minus 3 plus 4. At x equals 3.25, I got y equals 3. At x equals 3.5, y equals 3.5. At x equals 4, y equals 4. At x equals 5, y equals 4.5. At x equals 6, y equals 4.79. On the right, you can see the graph that we have. The red graph is our parent function of y equals log base 4 of x, and the blue graph is our transform function of y equals log base 4 of the quantity x minus 3 plus 4. Let's compare these two graphs. Our vertical asymptote of our parent function has shifted from x equals 0 to x equals 3. Our graph has translated to the right by 3 units and up by 4 units. Our domain from our parent function has shifted from 0 to positive infinity to 3 to positive infinity. And our range stays the same. It goes from negative infinity to positive infinity for both the parent function and the transform function. Here's a better look of our two functions, log base 4 of x, which is our parent function, and log base 4 of the quantity x minus 3 plus 4. All right, that's it from me. I will see you all soon.